Hello, this week we are going to start Unit 9. Unit 9, we're going to be talking about solution and colligative properties, which is the first thing we will do this unit. Then we're going to move on to gases, and then we're going to bring back stoichiometry at the end. So if you thought we were done with stoichiometry and moles, that is actually not the case. We are going to continue, so all of it is still going to build up from what we've been doing all semester. All right, so moving into solutions and colligative properties, hopefully this clarifies some of the reading material that you did on Friday. All right, so first we got to review molality. Molality is remember, a unit of concentration. So we did molarity last unit, and today for this unit, we're going to focus on molality. So molality is equal to moles over kilograms of solvent, and that's really the biggest difference that we're going to see right here. That we are going to be using kilograms of solvent, okay, instead of volume. We are going to be using mass. So we have some practice example questions here. All right, so for this first problem, it says, what is the molality of a solution containing 5.8 moles of sodium chloride dissolved in 17.4 kilograms of water? So I have my 5.8 moles. All right, so for this problem, it says, what is the molality of solution containing 5.8 moles of sodium chloride dissolved in 17.4 kilograms of water? So my equation, remember, is molality is equal to moles over kilograms of solvent. In this case, I have 5.8 moles in 17.4 kilograms of water. So my molality should equal 5.8 moles over 17.4 kilograms. So once I calculate this out, I should get 0.33 molal solution. All right, so that would be my answer for this problem. Okay, so for this example, it says how many moles does 2.55 kilograms of a 0.46 molal solution have? So that's the second problem here. And in this one, we're given the mass and the concentration. So in this case, we were given 0.46 molal. That's going to be equal to moles over kilograms. So we would have to multiply both sides by my mass, so that the number of moles for this example then is 1.2 moles. And that's our answer for the second problem. All right, the last example here says if a solution has a molality of 0.33 molal and has 12.0 moles, how much solvent is there? So in this case, we are given the concentration and the moles, and we are solving for kilograms of solvent. So we're going to set up our equation with our moles on top here and our unknown at the bottom. So we're solving for x. So in this case, we would solve both sides by x, so the x's here will cancel. I'm left with 0.33x is equal to 12.0. Divide both sides by my concentration, and so my x value here is 36 kilograms. And that's how you would solve that third example. All right, so colligative properties. So what we're going to be the reason we did molality is because we're going to use molality to look at the different colligative properties that we can see in terms of freezing point depression and boiling point elevation. So, for example, what does the DOT do when the roads are going to get icy in the winter? One of the main things they're going to do is they're going to see that they're going to put salt on the roads. When your mom's cooking, she's going to add salt to the pasta as she boils them. There's a reason for that. All this has to do with the colligative properties of the solutions. In the first example here with the DOT, our solution is going to be the water, the precipitation that comes down in the form of snow, and as it melts, it's going to melt and dissolve the salt. So what that does, it ends up depressing the freezing point of the water, so it makes it harder to freeze. Whereas if your mom's cooking pasta, she might put salt on that water, and that solute, that adding of the salt, is going to make the water boil at a higher temperature so that the pasta can actually cook more efficiently and faster. So both of these have to do with colligative properties, and that's what we're talking about when we talk about colligative properties, are the effects of solutes on the behavior of the solvent. And so for our intents and purposes for this course, we're going to mainly focus on water as the solvent. So anyways, when an ionic compound is added to a solution, remember that they're going to dissolve and ionize. In other words, they're going to separate out into individual atoms. So for example, if we had sodium, we'll call this sodium here, okay, and chlorine, right? So this is NaCl, and we want to drop these in to a solution of water. So this is water, and this is sodium chloride. Well, when we do that, remember that when we dissolve, these two compounds will separate. So you're going to end up with a bunch of these positive ions floating around, and a bunch of these as they dissociate. All right. So when a compound is dissolved, if it's an ionic compound, the ions will separate out into their individual ions as they dissolve, because remember that water comes in between them and is going to end up separating out the ions from the compound. So when we are looking about ionization, in this case, sodium chloride can ionize into two compounds. So in this case, sodium chloride will ionize into sodium ions and chlorine ions. So when we're asking here in the next question, what ions will the following ionize into? When we talk about sodium chloride, well, this will form, let me change the color here so it's E to Z. This will form two ions. Okay. For lithium oxide, it's going to be a little different. For lithium oxide, it's not just two compounds. You have two lithium ions and one oxygen, and they're all going to separate out. So you're going to have two lithiums and one oxygen, so this is going to separate into three different ions. Again, two lithium ions and one oxygen ion. For calcium fluoride, the same thing. I'm going to get three ions. I'm going to get one calcium ion and two fluorine ions. For aluminum sulfate, I'm going to get a total of 5 ions, because I'm going to get 2 aluminum ions and 3 sulfate ions. Now this last one is a little tricky. Okay, C2H4O. Okay. Remember, when we talk about dissolving and ionizing, we're talking specifically about ionic compounds. Covalent compounds will not ionize when they dissolve. They'll just separate from each other. So one compound will separate from the other, and that's what causes that dissolving. But these will not separate out. Okay, so the carbon, the hydrogen, and the oxygen will remain together. So they will actually only form one compound. Okay, so in this case, there is no separation. Why? Because this is a covalent compound. Covalent compounds will always have this value of 1 when they dissolve. All right, so colligative properties are the properties of aqueous solutions that depend on the number of particles dissolved in solutions. So that's an important part right there. It's the number of particles. So just remember that when we're talking about number of particles, we are talking about moles, because that's how we count particles in chemistry. So substances that ionize in water is going to equal to the number of particles that are the total amount of ions produced. So we have to not only account for the number of particles, but the total amount based on ionization if it's an ionic compound. So for example, again, substances that do not ionize in water, there's no dissociation, so it's just one. This is basically what we were just talking about in the previous slide. So hydrochloric acid, remember, it's an ionic compound because it's an acid, and so that'll ionize to 2 particles. Magnesium chloride, 3 particles. We're going to have 1 magnesium and 2 chlorines. And then for glucose, or C6H12O6, this is a covalent compound. So there's no dissociation, and again, it's just going to be a value of 1. So the 2 properties that we're going to focus on when we talk about colligative properties are boiling point elevation and freezing point depression. So boiling point elevation is the change in temperature required for a solution to boil. All right, so again, it's the change in temperature, whereas the freezing point depression is the change in temperature required for a solution to freeze. So those are the 2 values that we're going to focus on. For our intents and purposes, boiling point elevation, or normal boiling points for water, is going to be 100 degrees Celsius. This is going to be an absolute value, so it will not play into our role of calculating significant figures. Normal freezing point for water, remember, is 0 degrees Celsius. Again, an absolute value. We do not consider this as part of our significant figures calculations. All right, so what's going to happen? Solids are going to raise the boiling point, and they're going to lower the freezing point of the solvent. All right, and each solvent has a different molal freezing point depression constants, we call those KFs, and molal boiling point elevation constants, which are called KB. So these 2 are going to vary depending on the solvent. Again, for our intents and purposes, for our course, we're only going to be focused on water. So in that case, for water, all you have to know is that, all you have to know are KF and KB values of KF is 1.86 degrees Celsius times kilograms per mole, and KB is 0.512 degrees Celsius times kilogram per mole. All right, so those are our values for water. Remember, these values are strictly only for water as the solvent. Now, what you're going to do to find your new boiling point is, once you calculate these out, you're going to add that value, that boiling point elevation, or that boiling point or freezing point depression, into our original values of 100 degrees Celsius for boiling point and 0 degrees Celsius for freezing point. So we have these 2 equations here, freezing point depression and boiling point elevation. Okay. Where delta TF, or freezing point depression, this is the change in temperature in which the new solvent will freeze, is equal to I times KF times molality. So I just represents the number of particles, or the compound that the compound's going to ionize into. Again, for ionic compounds, you look at to see how many ions that will produce when it's in solution, and for covalent compounds, it's always a value of 1. KF is the freezing point depression constant, and KB is just the boiling point elevation constant. So if you know molality and you know the compound you're dealing with, then you should be able to solve these pretty straightforward. So let's look at a couple examples. Okay, at what temperature does water freeze, and what temperature does water boil? Well, we know that it freezes at 0. Oops. All right, so the first example here, what temperature does water freeze and water boil? So it will freeze at 0 degrees Celsius and it will boil at 100 degrees Celsius. Remember that these are values that are given, they're knowns. We're not going to use these as part of our sigma calculations. All right, number 2 says calculate the freezing point and boiling point for an aqueous solution made of 50.0 grams of sodium chloride dissolved in 8.00 times 10 squared milliliters of water. Recall that the density of water is 1 gram per milliliter. All right, so it sounds like a lot, but it's really not. We just got to take this a step-by-step process. All right, so first, we got to convert grams to moles. Remember, when in doubt, convert to moles. There's nothing that we can do if we are not working with moles. Now remember, I'm not going to round until the end. And I'll define what I mean by the end in just a second. All right, so now I found the number of moles of sodium chloride. What did I do? I just found the number of moles of sodium chloride that I have given my mass. Why did I do that? Because I'm trying to find the boiling point elevation and the freezing point depression here. So before I can do that, I know I'm going to need a concentration here. Well, I'm given the mass, which I've already converted to moles, and I'm given the amount of water. Now, the water is given to me in milliliters, so I just need to make sure I convert this to kilograms. So that's easy because it says, recall that the density of water is 1 gram per milliliter. So I know that there's 800 milliliters. I know that there's 1,000, oops, excuse me, not 1,000. I'll convert it to liters. This is 1 milliliter is equal to 1 gram. And I know that 1,000 grams is equal to 1 kilogram. Oops. So this is equal to 0.800 kilograms. What did I just do? I figured out that 800 milliliters of water has a mass of 800 kilograms. Now that I have mass, I have moles, I can find molality. So I know that molality is equal to 0.855578371 divided by 0.800. And my molality now is 1.07 molal. Okay. So I have found the concentration. This is what I was trying to do. So this is where sig figs are going to play. So I have 3 sig figs here because I have 3 sig figs in my mass. All right, so now I have found my concentration. Why did I need my concentration? Because I need to plug it into my 2 equations. In this case, I'm looking for freezing point. I'm looking for, ooh, I did it again. I'm looking for freezing point and I'm looking for boiling point. Okay, so for those 2 equations, that's what I am looking for. So I know for my freezing point, I have negative delta TF is equal to I KF times molality. So I have the compound sodium chloride. Sodium chloride will ionize into 2, so I know I value here is equal to 2. It's going to give me 1 sodium and 1 chlorine when it dissociates and ionizes or dissolves in water. So I know I'm just going to plug this in as 2 times my constant, 1.86, times my concentration that I just calculated of 1.07. That gives me a negative delta TF value of 3.98 degrees Celsius. Divide both sides by -1, and I get delta TF is equal to negative 3.98 degrees Celsius. So now this only tells me my freezing point depression. I have to add this value to my original freezing point. So my original freezing point is 0 degrees Celsius, and I'm going to add a negative value, so that's just minus 3.98 degrees Celsius. So my freezing point now is negative 3.98 degrees Celsius. All right, that was part 1. My boiling point can be calculated using delta TB is equal to I KB times my molality. My value for I is still the same, so delta TB, because it's sodium chloride, is still 2. My value here for KB is 0.512. And my molality is 1.07. When I calculate this out with sig figs, I get 1.10 degrees Celsius. Again, this is not new boiling point. Okay. That's not it. This only tells me by how much my boiling point is elevated. So I need to add this value to my original boiling point. So my original boiling point is 100 degrees Celsius. I'm going to add a positive 1.10 degrees Celsius. So my boiling point of this solution is 101.10 degrees Celsius. And that is my answer here. Okay. All right, guys. Hope you guys enjoyed this, found this clarifying. If you have any questions, again, you can contact me via Canvas, send me a message. I'm also on the conference online, so just look out for those announcements on when I'm going to be there. Again, just if you have any questions, let me know. Make sure you're keeping up with your work. Have a great day. Make good choices. Don't get arrested. I'll see you guys next time.